Alright, this example is on Faraday's and Lenz's laws. This one's more Faraday than Lenz, but regardless. We have a stationary square loop with length of side B, which is lying in the xy plane as shown, and in a magnetic field that is changing with time. It's sinusoidal B0 sine omega t in the z direction. Find the induced EMF, electromotive force, between the two terminals as shown. Okay, so the idea here is that when you have a loop in a magnetic field and something is changing, so it could be the loop size, the area, it could be the angle it makes with B, or it could be B, the magnetic field itself, then you will have an induced EMF, electromotive force. So in this case, the loop is stationary and it's the magnetic field that's changing. So Faraday's law says that the induced electromotive force is related to the derivative in flux, the time derivative in flux, the rate of change that is. So let's figure out what the flux of this thing is. So flux is, of course, the integral over S, the loop surface area, of B dot ds. Okay, now, in this case, B and ds are parallel with one another, right? And so this integral is very simple. It just becomes B times S, which is B times little b squared, right? The area of a square. And what is B? B is this B0, so I'll just put B0 then times little b squared sine of omega t, like that. Okay, so that's our flux. And then Faraday's law says that the induced EMF, so I'll write that as V of t, the induced EMF, is the negative. Actually, the negative is due to Lenz. That's the Lenz law part of this. The derivative of the flux, that is the time derivative of the flux. And so that would be the negative derivative of B0 times B squared sine omega t over dt, like that. Okay, so we calculate that derivative. When we take the derivative of sine, we get cosine, right? And then from the chain rule, we have an omega that comes down in front. So this would be negative b0 b squared omega cosine of omega t, and that is the induced EMF.